Okay, so we have seen that the matrices can undergo similarity transformations, and certain matrices there are special similarity transformations which it's possible to find for certain matrices which make them diagonal, right? But we also said that not all matrices are diagonalizable. So in this lecture we will look at the conditions for diagonalizability. When is a matrix diagonalizable? Okay, so consider an n by n matrix A. So you have all these elements of your matrix, right? If it has n linearly independent eigenvectors, it can be diagonalized by similarity transformation, right? But there are matrices which don't have n linearly independent eigenvectors, right? And they are called defective matrices. And so defective matrices are not diagonalizable, right? So we won't go into a rigorous proof of any of these statements, but we will collect together a bunch of facts which pertain to matrix diagonalizability, right? First of all, there is a simple sufficiency condition. We have already seen that if a matrix has all distinct eigenvalues, then for sure its eigenvectors are going to form a linearly independent set, guaranteed. So for sure any matrix which has all eigenvalues distinct, for sure is going to be diagonalizable, right? So this is a sufficiency condition. So the roots of the characteristic equation in this case is going to be all roots are going to be simple roots, so there will be no repeated roots, right? That's what this is. This is a sufficiency condition. Now a general necessary and sufficient condition for an n by n matrix is that it must have n linearly independent eigenvectors. So in other words, it must be not defective, right? So the statement that a matrix is not defective is the same as the statement that it is diagonalizable. Whenever a matrix is not defective, meaning it has n linearly independent eigenvectors, then we have seen by construction that you can stack together all these linearly independent eigenvectors and diagonalize this matrix. And it's also true that if a matrix is diagonalizable, then it has n linearly independent eigenvectors, and if it has n linearly independent vectors, it's diagonalizable. Both these statements are the same, right? It's necessary and a sufficient condition. Now there is a class of matrices which is very important and appears a lot in quantum mechanics, for example, which is the class of matrices which are not only diagonalizable, but they are diagonalizable by a unitary transformation, right? So the necessary and sufficient condition that an n by n matrix can be diagonalized by a unitary transformation, you can find a unitary matrix, is that A must be normal, right? Again, the proof of this statement is not necessarily very difficult, but it's somewhat technical, and so we will skip this proof, right? So we will just learn this as a statement that if you have a normal matrix, so what is a normal matrix? So we already saw, right? I mean, the arguments which would go into the proof, some of which we have already seen. Whenever you have a normal transformation, it means, and if there are two distinct eigenvalues, then the eigenvectors corresponding to these distinct eigenvalues are going to be orthogonal to each other, right? So that's the property. It's a stronger condition. It's not just that you have a bunch of eigenvectors which are linearly independent, but in fact they're going to be mutually orthonormal, and you can always so they're going to be orthogonal, and then you can normalize them and so on, right? So, and the special case that one has to be careful with is when you have degeneracy, right? So a normal matrix, even if it is degenerate, can never be defective, right? That's what this is saying, right? Not only is it not defective, but in fact it is diagonalizable by a unitary transformation, meaning that not only if you find all the eigenvectors, you can just put them together in a suitable way, or orthonormal set, and then you get a unitary transformation, right? So it's not just a similarity transformation which diagonalizes it, but it's a unitary transformation. So it seems like this condition for normality is a rather strong one, but these are very important. This is a very important class of operators and matrices, right? And a subclass of this is Hermitian matrices. We have already seen Hermitian matrices where not only do you get a full complete set of eigenvectors, orthonormal and everything, but also the eigenvalues are real. So in fact, unitary matrices are also another kind of normal matrices. We have seen these, right? You can go back and review this. So, but the result I'm just stating here is that the necessary and sufficient condition, which can be proven rigorously, is that an n by n matrix can be diagonalized by a unitary transformation if and only if that matrix A is normal, meaning it commutes with its Hermitian conjugate. So any matrix may can be brought into a form called a Jordan normal form. If you cannot diagonalize it, what is the next best you can do, right? And that is what the Jordan normal form is, right? So just for, in the interest of completing this discussion, we will include a very short description of what this is. We'll not go into the details of how to actually implement this and so on. I'll give it to you in the form of just one example. So any n by n matrix for sure can be brought into a form like here, where it's not going to be, it may not be diagonal, but it's almost diagonal. So you have elements, so the entire matrix is filled with zeros except along the diagonal, for sure. That's where you have the freedom to put in the information, but also you allow yourself a bunch of ones in this super diagonal. So this can be a 1, this can be a 1, all the elements in principle along this super diagonal closest to the, just above the principal diagonal, you can allow for a few ones, right? So there's another way of thinking about this. Think of this, consider a 6 by 6 matrix. I'm looking at a 6 by 6 matrix. It has one eigenvalue lambda 1 with degeneracy 2. It has degeneracy 2 but only one eigenvector, right? You may have degeneracy 2 and 2 eigenvectors, that's possible. But if you have degeneracy 2 and only one eigenvector which you can find, and then you have a non-degenerate eigenvalue lambda 2. Lambda 2 is a safe eigenvalue, but there is a triply degenerate eigenvalue lambda 3, right? But with only two linearly independent eigenvectors. Here you have the choice that you may have just 1 or 2 or 3. If it's all 3, then it's like it's like a usual case. But just to illustrate what happens, in this somewhat complicated case, I've taken this to be triply degenerate, but let's say you have two linearly independent eigenvectors, then we'll be able to put it in this form. There is a similarity transformation you can find such that you can put it in this form. The first block corresponding to the eigenvalue lambda 1 and lambda 1, since you can find only one eigenvector, 1 will appear here. If you could find 2, then you could also make this also 0. The second eigenvalue is, there is just a single eigenvalue, so of course it's just lambda 2. Now the third eigenvalue, the first pair has only one eigenvector, right? You can form a block like this. If you had all three eigenvalues had only one eigenvector, then you would think of this as a 3 by 3, and then you would put another 1 here. You can bring it in that form. But on the other hand, you have an eigenvector corresponding to these two eigenvalues, a single one, and there is another eigenvector corresponding to lambda 3, which you can think of as, for the purposes of this type of a treatment, you can think of this as another eigenvalue since it has its own eigenvector, right? Although you have lambda 3 and lambda 3, right? So this is the next best you can do, and the theorem states that you can always do this, no matter what your matrix is like. It can be defective. Of course, if it is not a defective matrix, we all know what the Jordan normal form is. The Jordan normal form is what we call the diagonal matrix, right? There is a similarity. We have proved a stronger result. You don't need these ones; they'll all be zeros, and you can bring it to the diagonal form. And the Jordan normal form is the next best you can do, which is almost diagonal, and it has, its usefulness in certain contexts. And primarily, its importance is in, when you are trying to understand how general these results are, right? But for our purposes, we have to be aware that there are certain matrices which are defective, and then you may not be able to diagonalize them. But the matrices that we will commonly work with, particularly in physics, are matrices which are diagonalizable. And when they are diagonalizable, they are this procedure has been laid down, and we'll see briefly what advantages diagonalization gives in the next discussion. Thank you.